So to clarify, then I just want to reinforce that this demo is going to demonstrate beta functionality that's beyond the release functionality of linear static stress. So this is our assembly geometry. One of the things I've done already is that I want to have a contiguous mesh traditionally between the seal and like the pins as well as the header. There's different ways you could do this modeling. You could also model those interfaces with frictional contact, but for this first setup, I wanted to model it as if it was contiguous. So I did the workflow where I imported my CAD geometry. I had a whole bunch of different parts. I went to my assembly mode, and then I used the Boolean merge operation to merge all those parts into a single part with multiple cells. So if I color this by cells, you'll see that there's, I think, 14 different cells, but they're all part of a single part. And so we utilize that information to then build essentially a weakly enforced contiguous solution. If I go to the property module, you can see I've already assigned some materials here. But if we look at, say, like the alloy 52 material, which is used for the pins, I've got mass density if I want to do a true thermal analysis, or if I want to do like a implicit dynamic analysis, I could use the mass density for that. Here I just got a temperature independent elasticity, but I've got an expansion coefficient, which is constant, and then I've got my metal plasticity. For my 304 L bar, I've got my temperature dependent plasticity data, as well as temperature dependent thermal expansion. And then similarly for the glass, I've got temperature dependent expansion coefficients. So again, UEL mat allows us, the UEL mat connection between Coreform IGA and Abaqus is what allows us to then utilize these material models directly from Abaqus. So if you already have material models, you don't have to worry about changing them or converting them to a different solver. And then I ran 3 different steps here, essentially to cool this from where the seal is being set in down to room temperature, and then cooling it and heating it through like a thermal cycle. And these are static general, but these have nonlinear geometry. And then I'm using the unsymmetric solver for these due to the nonlinearities of this problem. To then enforce or remove the rigid body modes, I have a distributed coupling between a reference point and then this outer annulus surface here. So again, this demonstrates the ability of Coreform IGA for Abaqus to utilize traditional reduced order model approaches such as couplings. And then I've applied my boundary conditions, again, just applying a boundary condition to that reference point of my couple, and then applying a predefined field that then changes over time for that global temperature. So it's essentially assuming kind of a thermal soak for that load condition and a uniform distribution of temperature. And then the last step here is going to be defining the mesh. And what I want to point out is, so here I've set my model up that I could now automatically build just a mesh on this. And so the pink regions will automatically tep mesh and the yellow region will hex mesh. And some of the challenges you'll see is that just because those elements are incompatible, normally you'd throw in tie constraints between those interfaces. And one of the challenges with the tep meshing is if I don't do any defeaturing, we'll end up seeing is that I really care about trying to predict whether or not my seal is going to crack. And I care about the interfaces between the pins and the header and the seal to see how those interfaces affect whether cracking is going to occur. But with body fit meshing, majority of my elements are actually not going where I actually care about them. I'm spending a lot of element budget on a thin region of my geometry that really doesn't matter. So this is where even with traditional tep meshing, you'd likely still want to spend time cleaning up this model just so that you have a more efficient solve. That I want to put more elements in this region. And of course, I might decide that I want to build a hex mesh on these pins. And so then that takes more manual time for me to then define that hex mesh on those pins to get that right. If I want a more structured mesh to have a more uniform result on my seal, I'm going to have to spend time partitioning my seal for that. So those are just some of the engineering considerations that occur with traditional finite element methods. But here I'll go ahead and delete my mesh and I'll show you what Coreform IGA for Abaqus allows us to do. You can see here, this is the Coreform IGA for Abaqus custom application that we ship. And there's a button here to create Coreform IGA meshes. I can just click that button. And then inside of the GUI dialog here, I can just insert a target mesh size. I can preview that mesh size. If I want a finer mesh, I can define a finer mesh. Right now, we do only support global mesh sizes, where we currently are working on adding local adaptivity. And in fact, since the release of this of Coreform IGA for Abaqus on our internal development branch, we have merged our local adaptivity capabilities. So that'll be something to keep an eye out for in the future. But this mesh looks good to me. I'll just go ahead and say, okay, you build that mesh. And that's it. From a user perspective, I'm done building my mesh. I'm done meshing. The next or last step for me to do is just to create and submit my job. Here I've already created a job. So I'll just edit this. And I can essentially just choose to run, say, parallel for Abaqus and parallel for the volumetric trimming operation. I don't have time to run this analysis during this call, so I've pre-computed the results, which we can look at in the visualization module. Let me turn off my mesh real quick. So this is an initial release. So we are trying to kink out or work out some kinks in some of the user displays. But if we look here, you can see my background grid on top of my simulation result. I've created a cylindrical coordinate system. So here, looking at the radial displacement of my header geometry at the final time step, and also look at then, say, my stress. Maybe I want to look at the max principal stress, and maybe specifically I want to look at it in the glass seal. And then given the millimeter ton second unit system, I want to set my bounds here to 35 megapascals, the maximum value. And so based on a kind of a simple 35 megapascal tensile stress failure criteria, I can start to see that I've got some regions that are essentially saturating at that tensile stress. So I might expect to see cracks occurring at some of these gray regions. You can see those are still really tightly bounded to the circle or to those holes. So something to definitely watch out for, but I can start to see an entire region connecting two of those holes. So that's just the ability to use Coreform IGA for Abaqus to set up a model, analyze it, and look at results.